Welcome to Quantum Kinetics First Diffusion, Season 3, Episode 5. I'm here with
Jason McCoy.
Jason, welcome back to the show. What are we going to talk about today?
Well, I'm really excited about today because we're really going to talk about the core principles of what the Quantum Kinetic Well is.
Great.
And what it does. But before we get into all that, we're going to start off with some Q&A.
Great.
Talk about the work with Victor Schauberger.
Oh, okay. What about Victor Schauberger? What's he known for?
Well, he is known for originally creating systems to move logs with water in like a logging operation. But what he discovered and what he observed in nature is the way that the water swirls and the vortices work, and how that relates to the quantum kinetic well, spirals and spiraling vortices of water.
Yeah. So Victor Schauberger totally worked on the logging flow to make a commercialization of that in industry.
Yeah.
And what he did there was his big thing was he always liked to watch nature because he would always go out in the woods and do long walks. And he was always looking at swirls and ponds and creeks and all this. And when he realized that if he made a dimple in the wood, as the log was going down the stream, the dimple would actually cause a vortice up on the log, so the log wouldn't scrape down the wood so much.
In the actual wood or in the basin of the
basin of the wood.
Yeah.
And then it would make a swirl up momentarily and then lift the log up.
Right, which makes sense. You know, you sent me the video earlier today, and I was looking it over, and one of the things in the video is they say that when he submitted his work on that, they ignored it.
Who's they?
Well, the academic community, because he was not a man of letters. He didn't have the degree in it.
So he didn't have a PhD or any of those things?
Which is so crazy because they ignored the observations of the universe, of physics directly, because he didn't have the credentials.
Well, I mean, isn't science...
I bet you can relate with that, right? I mean,
well, yeah, I can. I mean, most people can. I mean...
Yeah.
If you're not in the club, you're not in the club. And if you're out of the club, you're not going to get in the club. But like if you're a scientist's job, and if you actually look at the definition of science, is basically the act of observation and describing what you just see in either mathematics or actually just visually writing down what you see. Yeah. The can is red. The arc reactor is blue. Like that's science. You're observing the universe. Or a bee goes to a flower. So why would the academic community, and by the way, Victor Schauberger is very new to me.
Yeah.
Very, very new to me. And the more I learned about him, I was like, whoa, he was right on the money with all his vortice swirls and the mathematics of the rings that and his son was able to calculate the ring vortices to make the swirl like basically a galaxy down, like the quantum well.
Yeah. Yeah, that's what it reminded me of. Like when you look at the galaxy and you see that spiral, it's like you're looking straight down on a vortice, like a water vortice.
Right? Yeah, and actually the arc reactor rings, if you actually measure the rings of this thing, you can actually kind of begin to see the vortice swirl of basically Victor Schauberger in the rings.
Huh. Well, that is exactly what the first question was from the audience, which was, does your device utilize implosion or vortices a la Victor Schauberger? So what are implosions and what are vortices in this question?
Yeah, so Victor Schauberger, his big thing was that cavitation and implosions is life and explosion is death. That was his big thing that he liked to say. No one liked him saying that, and so the reason he said that is because of observation. One of the swirling mechanisms that he made is that when it would funnel down, just like a trumpet horn, it almost looks exactly like a trumpet horn.
Yeah.
And once the water would go to the center section where it's kind of straightened out, there would be this like double helix pulsing. There was like two pulses in the swirl that looked exactly like a DNA structure.
Wow.
And so he was basically, his conceptual understanding of the universe was that when you start the swirling action, the vortices, at a macroscopic level, the microscopic level then gets triggered in a very special way to create the double helix.
Wow. You know, it's so interesting. I was thinking about this on the way over here, which was that it seems like inventors and observers of nature find the idea in one thing, but it relates to another. Like you can see the swirling vortices in the water, but that's the same thing that happens in a galaxy, and the same thing that happens in the quantum kinetic well.
Right.
And that is just no wonder we have to find it in one category, but then when you apply it to another, like 10 years later or 20 years later, somebody else goes, oh, that thing that this guy did for water relates to like what you're doing for quantum
fusion.
physics. Yeah,
for fusion. And it's very cool to talk about why the swirling action is so critical to making galaxies, to making DNA, to making like the macro and the micro is the same, is that what they discovered with when they go into a river, and you know how rivers, they're kind of curvy and they kind of cut into the land, kind of like a vein. It looks like an organic vein. Like if you've ever flown in a plane and looked down on the earth, you see the cutting. Yeah. And it looks like an artery.
Yeah.
And what they found is that they take the voltmeters and determine on like if the river bend is bending this way, they take their voltmeters, they can sense that there's more voltage in the water as it's bending around. But on a straight path of the river, the voltage is really low.
Why is that? Why would there be more sort of potential divergent energy in a curve?
Well, I think it has to do with an accelerational turn, like a centrifugal or centripetal turning action creates a mini vortex itself, which causes a voltage gradient. And so with the arc reactor rings, and we'll talk about these, is that when the electricity is being pulsed, it shoots up out. The coils then turn the electrons, called the Lorentz force, and it turns the electrons, and then the electrons start swirling around the electrodes like you're going around a bend of a river. And thus it creates even more voltage. Even though you have a small voltage in, it's like a trumpet. So when you are in music class and you have a trumpet and you put your lips on the trumpet and you go...
yeah, I never liked that about I know that was what I didn't know. I never got into horn stuff.
It's very gross. You have to clean it out all the time. Onto your enemy.
Yeah, the clarinet player is always that nasty reed and stuff. But anyways, I shouldn't.
But yeah, the oboe had anyway, we could diverge. But the trumpet, you'd put in a very small input signal. Yeah. And then the output signal is just enormous. Yeah. And so Mother Nature has used these mechanisms to cause planets to form, to cause galaxies to form, to cause nebula to form. If you're not using these amplification techniques, you're not going to get, planetary formation. You're not going to get cold nuclear fusion. If you keep smashing things together really hard, really with massive amounts of voltage and amperage, you're just going to get death. As Victor Schauberger would say, it's just death. Do implosion and you'll get life.
It makes so much more sense. It's funny about that shape, the shape of that horn, or the shape of the vertice, or not vertice, but
it's a vortex.
Yeah. So that cross section of that's the same shape as if you took the octaves in music. You take one octave and then double it and double it and double it and double it. You get this parabolic.
Is that an exponential curve?
Yeah. And that's basically like what's happening in that vortex. Is it's coming in nice and shallow, and then it starts ramping up to this very steep, almost straight linear.
So in music, when you're going up the keyboard, like from 1 to 12, right?
Yeah. Nice.
The sound, the sounds from, let's say, if you're on 1 to 12, is a doubling from 1 to 2.
1 to 1.
1 to 1 is a doubling.
When it goes all the way from 1 to the next 1, or 2 to the next 2, or 3 to the next 3.
Got it.
The frequency has doubled.
And if you were to put that on a graph, that would be kind of an exponential curve anyway, right?
Yeah, and that same curve shape, not coincidentally.
Yeah, it's funny. It's funny how nature mimics music a lot.
All over the place. More and more, I notice it. After these conversations and studying music theory so much, it's all about frequencies,
waves, frequencies, and vibrations. Got it. I got it down, buddy. I've been practicing.
Yeah, it's all about that. I mean, over and over again, though. even when you look at the shape of a DNA from above, the cymatic patterns are the same things. Now, why is that? Like, that can't be a coincidence. It has to be a shared.
It's an orbit.
It's an orbit? Is that what
it's because the DNA is one strand going this way and then another strand going another way, or trying to almost like chasing it.
Yeah.
And my postulation is that if you look at DNA from the top, you just look at this, you're going to get a sphere. You're going to get a sphere going, two dots following each other, going. In my theory is that matter and antimatter are doing the same thing. They're twirling around each other, like this. But if you were to do it this way, they'd be going like that, like a. And that's, by the way, this is AC. Whenever you have a circle where current is doing a circle like this, that's alternating current. It's just going woo, woo, woo. But if you turn it sideways, it goes woo, woo, woo.
Oh, right, yeah.
But you can't see the three-dimensionality of it, which brings us to the next topic, which is 2D waves versus 3D waves.
Yeah.
You want to talk about that?
Absolutely. This is the thing that this is why I'm so excited to do the show today. So there's what is that from the website?
So there's a guy on YouTube, and his YouTube's called Action Labs.
Yeah.
And I forget his name, but he's a really cool dude.
Yeah. So I've talked to McKane a bunch of times about how this stuff works, trying to understand it. And this thing that you showed me was like a breakthrough moment. I was like, oh, that's how you can pull stuff together. Mm-hmm. So it shows that the waves in the water take this ping pong ball and somehow magically, not magically, but obviously physics, it moves backwards.
So why don't you set up the audience for the actual experiment in normal mode? So in Actions Labs, he's got a basin of water.
Right.
And there's a metal ring hooked to a piece of foam in the water. And there's a ping pong ball in the water, and he has an oscillator on the top, which then makes the foam go up and down. And as he's doing that, the ping pong ball is being pushed away from the foam because the waves in the water are pushing it away.
The way that they overlap is pushing them away.
Yeah. But when he turns up the amplitude of the oscillator and then the ring starts like bouncing the foam really high up and down in the water, there's a new wave that appears. It's not a 2D wave where it's just going out like this, propagating this way, but it's actually propagating up and down now in the water. And then what happens? What happens next, Jason?
The ball somehow manages to get pulled back
towards the foam.
Yeah.
That is oscillating.
Yeah.
Which is totally counter.
It falls like into it. That's what made me kind of understand the idea behind the well. I was like, wait a minute. Okay, now it all makes sense. If the waves are going in such a way that the ball, the particle,
the electron
or atom
positron or whatever,
what would otherwise be getting pushed away or forced out gets basically pulled in,
sucked in.
Yeah. But
it's just a wave.
Well, I guess it kind of makes sense though that everything can kind of get bunched up into one spot.
Mm-hmm.
That's the well, right?
Yeah.
And then because everything's trying to get into a smaller and smaller and smaller spot, that's what basically like overcomes the Coulomb barrier, right?
Yeah. It's so essentially is the waves from the outside, they compress in on all directions, kind of like a cavitating bubble, and it compresses them all in with a basically negative wave. Because when you have a 2D wave, it just does a not longitudinal, but transverse waves like this on like an ocean. But if you have a 3D wave, you actually get a compression. You get a longitudinal wave in the wave. So you can have this transverse, but you can also have longitudinal waves in the water too.
And that kind of just like keeps crunching it and crunching it and crunching it.
It's the big crunch, like the quantum bounce phenomenon of the universe.
Cue the video.
I love that video.
Should we do a dance video sometime?
Maybe? You guys should check out the new merch for the Quantum Bounce music video, and we'll put it up here for you to check it out. But it's really awesome. Go ahead and get your stuff.
It's a fun song. I love it. I every time it comes by, I'm always like, oh, I'm gonna listen to it one more time. No, it's awesome. I mean, it's that video, that example was for me a breakthrough moment, because I was like, oh, I get why he calls it a well.
Yes. I
get why it pulls stuff together. Mm-hmm. And if it gets into a smaller and smaller and smaller place getting pulled together, no wonder it can fuse.
And that's what the shell of the arc reactor basically is like there's electrodes in the middle here, and then you have the coils that sit on top. And the way that the coils pulse, 1, 2, 3, 4, 5, like this, it swirls, whatever's trying to come out gets pulled back in. So it's almost as if if you were to watch the electrons flow through this, you'd get like a little orbital, like spheroid of just circulating electrons all the way through. They're just confused, and there's all this noise, almost like Jupiter. And it literally, you get them to swirl using coils with an electron gun on the bottom.
Huh.
It's really just nature's mechanism for stabilizing orbits.
And that's a superior way to create fusion than just crash up derby, right?
Well, you can do crash up derby, but you won't get very long extended durations of nuclear fusion. Like, for example, the stellarator, which actually kind of does the Schauberger swirling action, has a longer plasma duration than, say, a tokamak, which is interesting.
Yeah.
That the stellarator design is more efficient and holds it longer.
Because of the spiraling nature of
I think so.
Yeah.
It has to.
That makes sense. I mean, like a coiled rope or it would make sense that wrapping something around a central axis, even in a circular form, would be superior than just like, speeding it around in a racetrack kind of a thing.
Well, because like if you ever watch NASCAR, you got like 40 cars going 210 miles an hour and they're bumper to bumper. It's like a high-speed traffic jam, and one person gets out of line, 40 cars explode, right?
Yeah.
Half the field or a quarter of the field's gone.
Are those fast neutrons that hit the sidewall? Is that what that is? Like a car hitting the sidewall?
Would you see a NASCAR race explosion, like in cars crashing? That's what hot fusion's doing.
Yeah.
It's just going over, it's destruction. As Victor Schauberger would say, it's just basically explosions everywhere and no good.
You know what's funny? You sent me a picture of the Chinese reactor, and the whole side in all of those tokamak reactors, the side walls are just armor. Like it's just it looks cool. I mean, it does look awesome. It's like this super exotic metal that is absorbing everything that like flies off of it. Is that what that's for, basically?
Well, it's a containment. The walls are for containment, and then the electrodes are bolted in the inside interior.
Oh, right. Yeah.
But what they're supposed to do is they're supposed to have cooling containers that go around the shielding so that it warms up from the neutron radiation. And here's what I find strange is that if you look at how hot fusion's reactors are supposed to make electricity, they're supposed to use their fast neutrons to heat up water that's on the blanketed around the reactor. Neutrons are not really good at heating up water. They're good at transmutating water, not heating up water, which is a big question mark to me, because if you want to heat up water, use infrared energy. If you want to heat up water, use microwave energy.
Right.
Like these are the waves that you need to use for heating water, not neutrons.
Right. Not to mention they're cryogenically cooling the magnets. Also, the mechanics of that are so crazy. Like, you have superheated plasma and then you have super cooled magnets, all so close together. No wonder it takes so much energy and money to make those things.
Well, and here's the thing, the superconducting magnets, let's just say that this is like, a tokamak or something, and you've got each one of these black ring things are a superconducting magnet, right? And let's just say you've got plasma swirling inside here, right? And it's working, right? But what happens if, because this is getting infrared heated up and this getting, neutron flux, and now the beryllium, or not the beryllium, but I forget what the material is for the superconducting magnets, but it's just to say that those magnets start transmutating, because there's neutrons everywhere here. It's called a nuclear cross section that's growing in here. Let's just say that the magnets start weakening and they lose their magnetic flux. And it's not going to be the same from this one to this one, to this one, to this one. So you get a weak spot over here, and then it starts losing confinement in this area.
It sounds like it's going to be a problem.
It's going to be, dude, whatever they're going to do and they think they're going to do, they're going to spend all this money making this, and it's not going to work.
It strikes me as like the thing where, remember when they first made computers and they had these giant vacuum tubes in these giant rooms?
Oh yeah.
And the whole room was like the size of like a tennis court, and that whole thing was basically as strong as a calculator. I mean, is it possible that the hot fusion industry is just betting on, hey, we're going to start off making a big giant thing, then we're going to make it half the size and half the size and half the size, so that eventually they get magnetic containment down to such a small level that it is plausible. Is that what their bet is? Or, I mean, I know you're ironically asking you to speak for the hot fusion industry when you're the cold fusion industry, but what is it that they're exactly, how far can they take that technology before you run into that isn't the way that it works, so you need to try something different?
The analogy about computers with the vacuum tubes and being as big as a building or a football field or whatever. But yes, the computer has gone from that size. Now you can fit it in your hand with an iPhone.
Yeah.
And the processing power of iPhones and, Samsung's is amazing. And that, yes, the hot fusion industry definitely was trying to go that direction. But the problem is like, we can already do with cold fusion, we can already do sustained nuclear fusion with devices that are the size of your hand.
Wow.
It's already done. It's already patented. It's trademarked, copyright protected. It's already done. So whatever they do with their reactors, try to make them smaller, they're just going to end up having to copy the quantum kinetic well with the vortices swirling.
At a certain point, you got to use that technology, right?
And it would be advantageous for the planet if they just gave us a call and said, hey, look, you know what? You got it. It looks good. Let's go ahead and get moving. Let's get to market. Let's get this going within 3 years. It'd be good.
The thing about
but they won't.
the analogy of the big of old technology being bigger and taking more power. Mm-hmm. So that kind of brings to the next thing, which is the whole 1989. Oh. So I think I was telling McKane that I ran into somebody I know who was a quantum physicist.
Wait, what happened in 1989? Oh, go ahead.
But I said to them, I'm working on this project with a friend of mine. I'm an investor, and he's working on cold fusion. And the guy's like just about spit out his coffee, and he's like, that's already been done. It didn't work, and that's that basically. And I was sitting there like, oh, I wish I had McKane right here just to like jump in on the conversation and fill in the blanks on that. But in 1989, mm-hmm. I mean, think about what a phone was, a cell phone.
It was the big brick thing that you had like in the old BMW, the 3 Series, and like the California, the big brick phone.
Yeah. And then video games probably had to be like what, Pong or something close to that?
No, I think it was like it was just the normal Nintendo 64. It wasn't even the Nintendo 64. It was NES.
Right.
The Nintendo Entertainment System.
And on, right? And technology was just in a totally different place. So here we are.
16-bit.
That was 1989. We're like, what, 27 years later? Did I do the math right on that?
It's like 30. Yeah, it's been a while.
So
it's been a hot minute, buddy. It's been a hot minute.
Since then, 30 years later, I mean, technology has evolved and you've created something different.
Well,
right?
And here's the thing that technology, and this is what the pariah and the PTSD of cold nuclear fusion has done to the feasibility, possibility, potentials of cold fusion, is that they basically painted it with such a disgusting brush that even if you go near it, it smells so bad and stinks so bad. Even if you try with good intentions to make it not stink and prove its viability, you'll get crushed by your colleagues, your students, and everything else. And so for me, I came at this in the beginning back in 2012 and started out learning about other people that had tried to do this in the past and learned about all their mistakes, and then realized that if I do this a certain way, methodically and carefully, and learn from everyone's mistakes of the past, that maybe, just maybe, I can get it through the gates.
You're talking about your go-to-market strategy, basically.
Yeah, right? Prove its viability, prove that it's possible. Yeah. Not some pariah like the guy at the coffee shop's like, oh, it's just they've tried that. It's whole honky. Don't touch it. Well, if you're not going to touch something to try to make it better, it'll never get better, right?
I think it's just that reaction, nothing against that person, but just that reaction of like, I got that too with music theory stuff, with numbered music theory. Like, there's already numbers in music.
We don't need that, buddy.
Yeah, it's like there's already there is. I mean, I did the patent research on my own thing, and I was like, there were many things that were that, but if you do it a little bit different, if you create the electronics a little different, if you do the music theory a little different, it creates a massive difference in what it can do.
You know what's funny about that? Steve Jobs, I was just watching some YouTube stuff about Steve Jobs, and he says, we're not going to make the Macintosh better. We're going to make the Macintosh different.
Yeah.
And so that's the thing about this is we're not doing electrolysis. We're not doing electrolysis better.
Right.
No, dude, we're doing electrolysis different.
That's awesome. That's what I thought it was too. Like after, I thought it was just a different way of doing electrolysis. I'm like, oh, you're splitting the, like you're doing that, and then you're like, no, there's something totally different going on.
You want to know what the fancy name they call it in science?
What's that?
The PhDs, they call it magnetic connection reconnection.
Magnetic reconnection?
Yeah.
Why is it what's reconnecting about it?
Well, it's like the swirling vortex. It's the swirling in and reconnecting and creating an extra pulse that wasn't there before.
Huh.
It's a reconnection, which is what nature does.
Isn't that the way it always works? Like even in the Victor Schauberger, am I saying this right?
Victor
Schauberger?
Schauberger. Yeah. He's Austrian.
Okay. So there's a section in that video that it shows the way he created a plow for plowing a field.
Oh my gosh.
And it goes one way and then it goes
like alien technology, dude.
But that's what the new AI, like if you've seen the new AI designed engines, they're the fuel intake, they're all very organic looking, which makes sense for fluid dynamics, that you would have these curved surfaces that channel a fluid or air in a certain way to optimize it. Like it makes mechanical sense to do it like that.
Well, if we can show pictures of it, we'll try to do it. But in the plow that he had was it would first differentiate, it would split, and then as it was splitting the curve like this, then as it was splitting, it would S-curve back, but it was a smaller S-curve. So it's as if it had some kind of centrifugal motion, then that was caught and then re-amplified.
Yeah.
And then and apparently that plow was really good. And they used copper. They didn't use iron because the iron oxide would damage the soil and the biology.
Right.
And so they used a copper, which would then basically push ions back into it, which again is a voltage difference. It's all about voltage gradients to make things better and more efficient. It's like music. I mean, like you can take two notes and they impede on each other, dissonance.
Yeah.
You can take two notes. I'm learning, see?
Yeah.
You can take, you're learning Quantum Well and I'm learning music. This is great.
Yeah, exactly.
And then you can take two notes, which is a chord, or three.
Yeah.
And they can do amplification.
Yeah. It's so cool when you do that. That's why I'm always on you about learning, like playing more music.
Use the proper terms.
Use the proper terms and play more music. It's so cool though when you hear things like you'll pause for a minute, you hear the wah 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 wah, like, and you did that on you put reverb on when you're playing Twinkle Twinkle one time. It's so you feel it, you get it like in a physical sensory way. What that must be doing, what's going on with that stuff. It's so
well
cool.
Speaking of reverb, you showed me earlier something about mushrooms.
Oh yeah
which I never saw.
Probably we should clarify that. So there's a video of they put these electrodes or some kind of a sensor into mushrooms, and then they connected it to a thing like that plays music.
Little mushroom right here. Is this like a little mushroom?
Yeah, just about. And then the sound that it makes it sounds crazy. It sounds like what a mushroom would make. It's like bing bing bong bong bong. It just sounds like the trippiest like space music you've ever heard, and it's coming off the mushroom.
As if the universe already has its predetermined frequencies.
Yeah,
kind of like Schumann resonance at planet Earth.
Yeah, for sure.
And the vortices creating higher voltages. I mean, like even our brains are emitting electromagnetic radiation into the air. And we're also absorbing electromagnetic radiation. I mean, like our iPhones and our phones and the radio towers, the AM, FM broadcast networks, we're all getting hit by that radiation.
Yeah.
And it's got to be doing something to our brains and our thoughts, you know?
Yeah. When I was a little kid, a friend of mine and I got really into karate. He was into it first.
Jiu-jitsu or?
This was Shotokan karate. So it was really, this was like in the early 80s after Karate Kid. Everybody wanted to be karate master and whatever.
Wax on, wax off.
Yeah. So the conversation of like ninjutsu came up, of like reading each other's minds. And so we started trying to do that. And there was this one time when we tried to guess the number that the other person was thinking of, and I got 7 out of 10 of them right. That's a lot.
What? How did you do that?
Because we just sort of like, we practiced it for a while, and it was like after a while, somehow a connection seemed to happen where we were picking up on each other's thinking. And
did you sense anything when that happened? Were you feeling any higher vibration, or did anything hit you?
I would describe it more like it's a state of listening, not broadcasting, but listening,
absorbing.
Yes, it's not. And it's the problem is that our minds have so much clutter in them normally, so much noise. There's one for you.
I gotta pay my bills. I gotta get a girlfriend. I gotta blah blah blah. I gotta wash my car. And like that's noise, right?
Yeah, that is noise. A lot of it. But then when you can turn it all off, and you can just be present, and you have a sort of intent of connection, then you can seem to do that. It does make sense because our brains do emit frequencies. They could receive frequencies.
Ask and you shall receive.
Yeah.
I mean, when I figured out the discovery, I was on my knees crying, asking help. Like, I need help figuring this out. Please help. And then all of a sudden there's the answer.
Did you see, like you said that you had this moment where like things weren't working and you were just like at your wit's end and you just in a kind of a wreck, and then you got like a vision or a voice, or what was that moment when you're like, oh, I need to do it a little bit different? And why was it so different? I know you maybe can't speak to the specifics of what was different.
Feel it again.
Yeah.
And what it felt like was when you're at the lowest point and there's nothing that you don't even want to breathe. Like you just want to give up. Like you're done. It's like when you lose all sensation of feeling, then that's when you're able to pick up another frequency that's not there. Like people who go blind, for example, their tactile senses go up.
Yeah.
Because they're not using the visual part of their brain anymore. The other parts of their brain activate more.
Yeah.
It's as like that. So when you're at the state of lowest well energy in your mind, thoughts, something might reappear. Something might appear that you didn't notice before. Maybe that was already there. Maybe in your subconscious, you already knew the answer. You just were glossing over it, right?
Yeah.
Like trying to go through a book really fast and you miss the one golden nugget sentence.
Or you've done it, or you had tried it before. You know, I showed you my sketchbook today. I've been working on guitar diagrams for
7 books,
at least 7 sketchbooks just to guitar in probably 3 to 5 years.
And these are not like little journal books. These are like the big sketchbooks.
Yeah, and full. Every page, every day, I do a couple hours and like 4 or 5 pages of diagrams, just to find the simple form of it. Which, ironically, this is what. Like, I sometimes wonder if I'm a good inventor because I find the answer, or a bad inventor because it takes so much time. And like it's whittling it down to like all the stuff you don't need to the essence of what it really is at its most refined, elegant, finished form.
And that's what happened with Steve Jobs too. That's why all the executives hated him so much, because he was so iterative and so expensive and so time consuming. But when he got down to the basic, look, we're going to make a computer that's for a grandmother. Yeah. And everyone's like, why would we do that? No, you don't see the vision that I have. The vision of the future, you don't see it. And that's what you told me a year ago, that a genius is someone who sees the target and hits the target when no one else sees it.
Yeah. A skill is hitting a target nobody else can hit. And it takes a genius to hit a target nobody else can see.
And I love that quote. Steve Jobs, for sure.
I love that quote because, I mean, we do it too as the inventor. Like you stay in these, you get in these ruts and you're like, but like, this is what I understand. So this is what I'm going to try. And you just stay in the lane. And then perhaps from sheer like iteration, you eventually bump into or try something just for the sake of trying something different,
Mm-hmm.
and you're like, whoa, that's it.
Yeah.
I have to do something in a different way, or
And it's almost like Occam's razor, where the simplest thing is usually the best answer.
what does that mean? I've heard that metaphor before, or that
It's a theorem basically from an old ancient time, basically that like, don't make things complicated because you're just making it complicated.
yeah.
If it's like simple, like for example, the pen, NASA had to design this pen to work in zero gravity, right?
Yeah.
A pen works with gravity, right? Like
Yeah.
it pushes and then you write and then the ball opens and then it drops the ink on the thing. And so NASA spent all this time and money and engineering to make this zero gravity pen. And then when it came to the point where they had to do the launch and they're like, well, we didn't figure out the pen, they just handed him a pencil
Huh.
and said, just write it on graphite.
Right.
Just do it.
There you go.
Oh, bro, it's the simplest thing. Why complicate? Like with the arc reactor,
Yeah.
it's a $40 toy that can do cold nuclear fusion and emit thermal neutron radiation safely and consistently. It's a pen. Soul. It works. Why change it?
Well, that really speaks to the, like, you know, the design stuff. As a designer, like, you have these moments when you're designing, and so many times that design is found in nature, because nature and evolution, if you kind of go that route, that like a better design survives, and then that design iterates through procreation, and then some baby of that dolphin is a little bit more hydrodynamic, and then that dolphin, the next dolphin, and 20 dolphins later, you got a dolphin that's like super efficient, right? Or shark or crab or whatever, bird.
Yeah.
You know, and so it makes sense that
Or
it
human.
takes iteration. Or human, yeah. Yeah, true.
And what I've learned from this technology is that and this is kind of a little bit, and just take this with a grain of salt, but in my thinking of this technology, evolutionary development of like technologies does happen in some type of evolutionary state, even in the lab, even in nature, even in planets.
Even writing a paper or doing your taxes, you get better and better and better at it.
Yeah. And you learn new words, like you go use a thesaurus, you know, or for example, electronic wise, I had to get the dictionary of electronic, and it's like this thick, and it's super tiny font, right? And it's a dictionary of all electronic terms from, you know, A to Z. And I read through it. I continue to read through it. I'm learning all the time.
Really?
Yeah. It talks about radios. It talks about electricity. It talks about transistors. It talks about MOSFETs. I mean, this book is from the 1970s or 80s, and that dictionary has everything in it. It gives you all the baselines. And actually, when you write a patent, your objective is to use that, because that gives you the strongest source words to give you the most credibility. So if anyone writes a patent, that would be the way to do it. But anyway, going back to the evolutionary state of development, that yes, the technology stems from basic understandings.
Yeah.
I'm going to close the circuit. Okay, what happens if you close the circuit but then make an electron go a different way?
Yeah.
What if I make it go back inside itself? Plasma reconnection or magnetic reconnection. Oh my God, there's nuclear fusion. It works.
So that's what you did. You just kind of like, we're like, this is not working. I'm at the end of my rope. I'm going to try something different.
Mm-hmm.
And then you tried something different.
It's like an iteration. Like when you see 1, 2, 5 or 1, 2, 4, when you see that, your brain goes, well, what about where's 3? That's the first thing that your brain does. And deductive reasoning goes, where's 3? I got to go find 3 somewhere. 3 is really important.
Yeah. And that's sort of how you got to solving it, or was it just a total breakthrough, or was it iterative? It sounds like you hit a dead end and then you tried something different to get to that answer.
Yeah, it's like if I had done 1, 2, 4 and it was never linking. I was like, well, where's 3?
I see.
So it was just deductive reasoning. Well, if I can't do 4 and I'm doing 1 and 2, I don't know where 3 is. Yeah. Let's just try this random thing over here that maybe that'll work. And it did.
Yeah.
I thought it was going to explode. I thought as soon as I turned it on, it would just go. But no, it was like super stable, super cool electrolysis, super cool headache.
Yeah, you got to be careful with that stuff.
Yeah, the nuclear cross section of cold nuclear fusion at like household voltages is only like 4 to 8 inches of cross section, so it's pretty safe.
Wow.
And actually, when we were doing a study, and this is just when we were doing radioactive waste study, this is a great little story. But when we turned it on in their lab, and these people were like experts in nuclear, right? They're nuclear experts in isotopes. When we turned it on and showed them the X-ray emission and it was doing beta decay X-ray, one of the technicians, she ran out of the room. Like she was scared. Like she just ran out of the room. And I said, well, where is she going? And everyone in the room was like, I don't know where she went. But she came back into the room with this huge detector and ran up to the reactor and pointed it at it. And so she's standing next to this thing with this detector. I don't know what it was. I think it was a neutron radiation detector. And she was standing next to it, and then she turned around and gave us a thumbs up. And then she left. So she, like, when you do this technology and we show this technology to you, you may not understand what you're looking at, but there are professionals out there that go, holy crap, that's it. They won't say it.
I was going to ask you about that. You always show this one chart that has, like, it's a regular chart, and then there's, like, one red spike in the middle of it.
Yeah.
What is that chart? What is that red spike?
Yeah. So that is a chart emission spectrum from 0 keV or 1 keV up to 20 keV X-rays emission.
Is that, what is kilo
electron volt? So 1 is 1,000 volts.
Okay.
5 is 5,000 volts. And that's the amount of energy that the photon has. It's like you pull back the rubber band and you let it go, and it has that temperature.
Right.
And so when you hit 10 keV, that's 100 million degrees Celsius snapping of the rubber band for fusion. And that's when you know you're getting the emissions of fusion of X-rays.
So that's basically your way of saying, see, that signature would only be there if we were doing real fusion.
Correct. Right? And that red spike you see that's really, really characteristic and really high, that's an iron 55 sample for calibration, which emits a 5.8 keV and a 6.2 keV X-ray, which is called a characteristic X-ray. It's like a fingerprint identification.
Right. That
iron 55 is turning into manganese. It just lets you know what the beta decay is going on.
It's showing you that that's happening. So let me ask you a question that, like...
Which, by the way, is 55 million degrees. That's hot. That little sample is hot.
It sounds hot. This is kind of like a kick in the beehive kind of a question, but when you show those results and you can say, like, look we have this coming from a lab showing that this exceptional signature indicates that we're creating fusion, and you've done all of the things that you've done to establish your credibility in the subject, how come you don't get more credit from the industry in general for being first to fusion? I know you say that, and that's on all the videos and stuff, and you clearly have the information to prove that you've done it. But I see all these videos all the time. I send you them all the time. I send McKane like 3 or 4 videos a day practically of just like, do you know about this? Do you know about that? And he's like, yeah, I know about this. I know about that. But they're all fusion videos, and they're all these people saying like they're almost doing fusion and they almost got fusion. And I'm just wondering why they get so much press, and you already have the goods. Like you already have the signature that shows that you're doing.
But you really are kicking the
I'm
hive.
kicking the beehive.
I have to be careful how I answer this.
Yeah, go ahead. I mean, but I'm involved with this project to some degree. So I'm like, how is it that you're not getting more credit for really doing it? You know?
Yeah. I guess I'll just have this analogy to back in the 1880s and the 1890s when Edison had DC figured out, direct current, and he had all his buddies, and he was back to, he had the Edison company, and he was making money.
Right. Yeah.
And then this little punk ass kid called Tesla shows up as an immigrant, on the New York shoreline off a boat with basically no money in his pocket except a reference letter from an institute saying that he should go to the Edison Institute.
Wow.
And then he comes up with AC power, which, by the way, Edison screwed Tesla early on. So then he comes up, Edison kicks Tesla to the curb, then Tesla comes up with AC. And so there was this fight, like, I'm established, I'm Edison, and I'm making my money, and I'm happy, go Lord, and I want all of the transmission lines to be DC, which, by the way, if we went with DC, we would have transmission lines as big as houses, copper that thick, which is not efficient. But AC allows you to have a copper, a wire that's super tiny because it's just oscillating back and forth, AC electrons back and forth, and then they get consumed. So when you have a new tech that is better, but is a threat to an established organization or even an investment pool, like hot fusion has an investment of now, I think it's like $8.7 billion of, the last 2 years. It's huge. And by the way, it's ramping up just like the curve, exponential curve. It's going faster.
More money.
And so let's say you have a kid that shows up with cold nuclear fusion, like Nikola Tesla shows up with AC and says, hey, bro, don't make your copper wires this big. Make your copper wires this big and just use AC and it's all going to be good. What happened to Tesla? Not good. They didn't treat him very well, right?
They suppress it to protect the existing industry.
But then once he died in 1943, then they just were like, oh, yeah, we're going to do AC. It's all good.
Wow.
Once and also another thing, too, is so Tesla patented the radio first in the U.S. Then Marconi came over to the United States and then tried to patent it, but couldn't because Tesla already had the patent. And then a think tank came in with a bunch of money and changed the minds of the patent office and the basically legislature to remove Tesla's patents. So then Marconi and his think tank could use radio development for commercial.
Right. So
basically they stole the patents from Tesla and then made an industry from his tech.
Right.
And then when he died in 1943, then the Supreme Court said, actually, Tesla made the radio patent first and we're going to give him all the credit. After he died. This is how the world works.
Well, if you were to get funded to that much money, like I believe in this thought experiment. I believe in doing this, of just indulging in, if everything went right and you had a giant chunk of money and you could make the things you want to make. I just think it's so important to allow yourself to envision the best possible outcome, even if it's a long shot. What would that look like for you? What does that do to humanity? Yeah.
So the first thing that we would do is obviously radioactive waste remediation for nuclear fission plants. So we can keep electricity going for these nuclear fission plants.
For all the toxic waste.
For all the coolant.
Okay.
And all that. So we're basically a cleaning center for nuclear fission. And then we're also tertiary cleanup for the rivers too. So basically we're inside the nuclear fission reactors, cleaning your source coolant water. We're on the outside boundaries of the rivers, cleaning that water as tertiary cleanup. And then from that cleanup, we're actually mining materials from fusion. So we're using that material to basically make new age batteries with the carbon hydride materials, ion exchange materials. So as we're cleaning and helping, we're also creating a new industry. And from that money, we can go to stage 2, which is another technology base. And then from that, stage 3 to another technology base. And then eventually we just basically are all using nuclear fusion for industry, and Mother Nature will be happy. The dolphins won't have tritium water to swim in, and de-evolving. Actually, the radioactive waste makes animals de-evolve.
Really?
It kills them.
I thought it was the mutations basically like disrupt your DNA, and then you have like a
split.
Yeah, and then like the
it's a 50-50 split, actually. You can have mutation going good and you can have mutation going bad.
You just don't know.
It's a probability chance. Some of the material and the agriculture and the mushrooms, going back to mushrooms in Chernobyl, are actually growing better because of the radiation. And it's a 50-50 split. Some of it's really bad. Some of it's really good.
Isn't that amazing? Like some mushroom in some cold, dark, weird Russian nuclear facility,
shut down city town,
down in the basement, is growing better because it likes radioactive waste.
Yeah, there's some organisms that love radioactive waste, right?
Yeah,
that they live off of it. And actually, there's some studies for radioactive cleanup using biology as a form to eat the bad stuff.
Yeah. Well, it just goes to show you it can be broken down, and you can do it through technology. So what you're doing is the vision of helping clean, like Fukushima, right, in Japan, and Hanford in Washington State.
Yeah,
you have radioactive material, but the quantum kinetic well can basically treat it by breaking it apart or aging it faster.
Puts it in a time well.
And then that basically changes it from something that is dangerous to something that's basically inert or even useful, right?
Correct. And that's, I mean, take a bad thing and make it good, right?
Yeah.
That's what fusion does.
It's all chemistry. It's all physics. I mean, not chemistry, but in this case, nuclear. Well, it's kind of nuclear chemistry in a weird way, right?
What's interesting is that when someone says chemistry, I think of electrons just bouncing off each other and rearranging molecules, right? That's chemistry. It could be exothermic or endothermic, where you get hot or get cold. Well, in fusion, can't you get hot and can't you get cold? In a nuclear reaction? Okay, if there's a nuclear reaction, can you get hot? Yes.
Yeah.
In a nuclear reaction, can you get cold? Yes.
How cold? What does that mean, cold? Like relatively cold? Like relatively cold, right?
And this is where we're talking about gravity now. Like when you get nuclear reactions that are cold, you're doing something with time. It's a gravity well. You're beginning to do something with gravity when you're doing cold nuclear.
Huh.
When you're doing hot nuclear, and here's a great point that I've been waiting for this point for a long time, and finally we're here. If you can go up, you can go
down. Yeah.
If you can go forward, you can go
back. If
nuclear energy that's like a bomb, nuclear bomb, does what to people?
Radiates them.
If you stand next to a nuclear bomb, what does it do to you?
Vaporize you.
It kills you.
Yeah.
What if you stand next to cold nuclear?
Are you saying it could heal you?
I'm just saying, for every action, there's an equal and opposite reaction on the scales.
True. Yin and yang, Newton's second law of thermodynamics,
and that's as far as I'm going to say, but
wow,
there might be something to nuclear fusion that is more than meets the eye.
Wow. That's exciting to think that that's possible.
It makes
or to know
sense.
That it's possible.
It makes sense that if you do one side of a spectrum, you're going to get a result. If you do the other side of the spectrum, you're going to also get the opposite of that spectrum.
In so many ways that has proven out, right? Yeah. Yeah. I mean, it is in music theory and, harmony and discord, in philosophy, yin and yang.
Well, there's good, and like every Star Wars movie is about the dark side versus the light side.
Right.
Creation versus death.
Yeah.
How about that, right?
Yeah.
Harry Potter, the Philosopher's Stone versus, what was the bad guy's name in Harry Potter? The wizard?
I think it's Baltimore. No, Baltimore.
Baltimore.
I call
Baltimore. Yeah, the guy with the nose is all like this.
Yeah.
So the way that you look at the universe is that if you can sustain a little micro star, basically in your hand.
Yeah.
I mean, yeah, it's going to emit a lot of radiation like X-rays, which it causes cancer and all that. But what happens inside of it? Is there something inside that's going the other direction? That's maybe some kind of creational force, like the vortices of Victor Schauberger, where he said that the implosion potentially is creation versus an explosion is a destruction.
That's wild.
We went full circle, baby.
That is wild. We spun actually in a vortex full circle there. Yeah. No, it's so true. I love that stuff. It's studying waves and feeling music and learning about the things about physics from you and quantum physics and understanding the quantum kinetic well has taken probably, months, as long as I've known you and we've been talking about this stuff. Mm-hmm. And it keeps like layer upon layer. It keeps getting more understandable.
It's because your brain is evolving, Jason. Like your thoughts are becoming an idea, and then your ideas are becoming an action of understanding. And then you're like, oh, I understand this. There's a difference. And this is what Richard Feynman said, is like, there's a difference between knowledge and understanding.
Yeah.
Okay. And like, I can have knowledge of like physics. Cool. But do you have understanding of physics? And I can tell you that if you turn on nuclear fusion, you're going to get A, B, and C, and D. You're going to get those reactions because of understanding. I know that from experience. Most people don't know that from experience because they've never done that. They've never taken that path. Right? Yeah. And so when I say that it's going to do these things, everyone's like, where did you come up with that, weirdo? Yeah. No, this is from experience of understanding.
Well, for everybody else, myself included, it's abstract. That's why I'm always grilling you on like, hey, let's get a metaphor. Let's talk about, let me see a picture of it. Let me understand, that's why kind of going back to what we were talking about with that, seeing the ping pong ball in the water. Like, I could not imagine there's a way to make a wave that actually it ends up pulling something in towards it. When I saw that, I was like, that's it. That's the thing. Now I get it.
That's understanding. You now see Mother Nature do her thing.
Yeah.
In an experiment that was a piece of foam.
Yeah.
A ping pong ball.
Yeah.
And a ring on an oscillator.
But that did it. That did it. What was you once told me about an expression. You mentioned you were a former volunteer firefighter, right?
Yeah.
And there was some expression about not kicking open the door if you could, like, what was the thing?
Yeah, in the fire service, when you go to a call and there's someone in a room that you can't get into, usually you have your Halligan and you want to just break the door down.
Is that the battle axe thing?
Well, the Halligan's the thing that has a little, it's kind of like a crowbar kind of a deal.
Oh, okay.
But yeah, you can use the crowbar and like break the door jam open, essentially, which by just doing a little thing, or break the lock. But essentially the saying is, try before you pry.
Oh, I see.
So, like, if the door is already unlocked, just turn the knob,
Yeah, yeah.
And that's what nuclear fusion's like. It's like, dude, the electronics, you may have a nuclear fusion reactor in your car and you don't even know it. It's just operating, or a quantum computer is operating like a cold fusion reactor too.
Well, it makes sense that these things that exist in nature are, that we could do them too, but we need to do the design like nature does it. And that's what you always say, like, you don't have, like, what is it? You don't have to force it.
Fusion is love.
Fusion is love. Yeah.
And love is fusion. You don't have to force it. It just happens.
Why love?
Because, and we're going to close up here in about 2 minutes, but we'll end on this one. But the heart, they just found out that if you slice the heart in a very specific spot with an incision, you can unwrap the heart.
I saw that.
And you can, when you unwrap the pumping sections, it actually, when it unrolls, you have the atria, and then there's another part that goes out.
Mm-hmm.
And when you unwrap it, it becomes basically a Mobius flap, a Mobius strip that has one little turn in it. And then you can turn, it's basically a portal, a white hole and a dark hole, one coming in, one going out. But these ventricles that open up, you can twist them back in on each other to make the left ventricle and the right ventricle, and then the pumping action. And that's why I say fusion is love, is because the electrical power of the heart comes from basically another dimension that is all love. To pump the extra energy in, to make the heart go boom, boom. It pulls from another dimension and then releases. That's the love. It's a giving to make it go forward. That's what love is. It's fusion.
Wow. That explains the saying then.
Well, I mean, I had to give it to you eventually because I don't know how long I'm going to be on this planet any longer. So,
well, it's good to know, and it's. I'm sure everybody's wonders some of those same things of like why, like we talked about this before, but so many of the things that you've talked about, and I can say this from when McKane's editing the videos,
you're always hounding me on.
I know, and I'm
fix this, do that,
micromanagement
okay.
At level 10. But I just love good editing. It's like the videos have gotten so good, and
that's because of you.
Well, thank you, but you do a great job, and there's so many metaphors in there. That's one thing. If you're watching the videos, watch for these little Easter eggs, and that's what I love calling you about. I'm like, what is that? Why did you put that in there? What does that mean? And there's so much information in these metaphors, and it is true. It's like nature has a way of doing it.
She's also leaving tips and hints and tricks and stuff for you. If you just observe and watch, like Victor Schauberger, watch water fall down rocks. And, that if you're listening and you're like going back to the well and letting the receiver come in, you'll pick up on these new inventional ideas that Mother Nature has already figured out. She wants to give them to you, but you got to be listening. So
yeah, for sure.
I think we did a really good job of wrapping this up, man.
Absolutely.
So fist bump there.
Yeah.
That was really good. So thanks again for tuning in to Quantum Kinetics. We really appreciate it. And go ahead and make sure that you like, share, and subscribe. And thanks for listening all the way through. And again, fusion is love and love is fusion. You don't have to force it. It just happens.
There you go.
All right, Jason, thanks for coming on the show.
You bet.
We'll see you guys on the next one. Take care.